Hi, today I'll be explaining Book 4, Proposition 11. In this proposition, we are trying to prove that if you inscribe a equilateral and equal angular, that you can inscribe an equilateral and equal angular pentagon in a circle. Okay? So what we're given is a circle with the points A, B, C, D, and E. Okay? So our first step is drawing the triangle F, G, H. Okay, so we're just going to draw it down here, F, G, and H, okay? And we're going to be using Book 4, Proposition 10, okay? Which pretty much says that you can make a triangle where two of the angles equal double another angle, okay? So in this case, for this triangle, we say two angles of F equals angle G, or two angles of F equal angle H, okay? So our next step, this is step number 1. Our next step is to move the triangle into the circle. Okay, so we're going to move the triangle, or we're just going to copy triangle of FGH and put it into the circle with ACD. Okay, and this is just Book 4, Proposition 2, which says you can put a triangle into a circle. Okay, so I'm going to do that with a different color. Line here, with these lines, because it's hard to draw freehand, and right here, I'll fix that D. Okay, so now we can say the next step, step number 3, now we're going to be doing green. We bisect the angles C and D. Okay, bisect angle C and angle D, okay? And we're going to be making lines CE and DB, okay? And that's going to be using Proposition 9, Book 1. So I'm going to use my handy dandy ruler now because I like straight lines. Connecting here and connecting here, okay? So our next step is now to just be connecting all these lines together, okay? So you connect CB, line CB, BA, AE, and ED, okay? AE, okay? And then for that, I wrote 4 there. For that step, we're just going to be using postulate 1, la la la, and you connect the lines, okay? So I'm going to just quickly throw down these lines. BA, AB, AE, and ED, okay? Already looking like a great pentagon. Okay, so our next step, step number 5, we're going to be saying, so since, remember, we use the same triangle here and put it into the circle, it applies the same. So one of these two angles are equal to double this angle. So since we bisected angles C and D, that means that the angles that they split are equal to the top angle, okay? So because it's double that angle split in half, it's 1, yeah. Anyway, so we can say now that all those angles are equal to each other. So angle ACE is equal to angle E is equal to angle CAD D is equal to angle D is equal to angle ADB is equal to angle ADB is equal to angle ADC, or sorry, BDC is equal to angle, or BDC, yes, and then is equal to angle ECD. Okay, sorry, that's a lot of angles. Okay, so then because of, for that, our reason is going to be Book 3, Proposition 26, okay? Which pretty much says that if the angles are equal to each other, which we've already proved using the first triangle, so I'd probably say statement 1 as well. Because it has equal angles, it's going to have an equal circumference, okay? So with our next step, we're going to use that by saying if it has an equal circumference, it's going to have equal lines, okay? And that's going to be using book 3, proposition 29. Like I said, with this one, we said it had equal angles, which has equal circumference, and proposition 29 says if it has equal circumference, it has equal lines, so we can say all these lines are equal to each other. So CD is equal to CB, which is equal to BA, which is equal to AE, which is equal to ED. Okay? So our next step, CD, yes, okay, sorry, a lot of lines. Our next step is going to be saying that AB is equal to ED, okay? So AB is equal to ED, pretty much what we just said. But we're going to add lines B, C, D. C and D, okay? Because of this, it's going to be equals added to equals are equal. So since A, B, and ED are already equal, adding something to both of them are going to make both of them equal. So we're going to be drawing the circle just to show you, AB, B, C, D. Yes, okay. So this circle, or this circumference, is AB, B, C, D is equal to the circumference of E, D, C, B, okay? E, D, C, B. And for this, we're going to be using common notion 2, which pretty much says equals that are added to equals are equal. So these two circumferences that we made are equal, okay? So just an imaginary line to show you is here and this here, okay? So because of this, we can say that the angles BAE, angle BAE is equal to angle AED. And that is because book 3, proposition 27, which pretty much says if they have an equal circumference, then the angles will be equal, okay? So before we were just doing these little angles, but now that we're using the circumference of the whole circle, we could say that the bigger angles are equal to each other. So this angle here and this angle here are both equal to each other. So now our next step is just to say pretty much, Euclid doesn't do this so we don't have to do it, but pretty much he goes around and says each of those lines are equal to each other, therefore if we add a few lines to it we can make the circumferences equal to each other. So he goes around and keeps saying each circumference is equal to each other. So in the end, that makes all the angles are equal to each other. So we can say all the angles are equal to each other. So angle BAE is equal to angle AED, which is equal to angle EDC, which is equal to angle DCB, which is equal to angle CBA. 1, 2, 3, 4, 5. Okay? And we're just going to be using above as our reason, just to say we repeat all this. Okay? So with that, we can say that because each of the angles are equal to each other, and so if the circumference is equal, and the angles are equal, and the lines are equal to each other, we can say that we made an equilateral and an equal angular pentagon in a circle, which is our proof. So we can say QEF, and we're done.